Okay, we're going to wrap up section 6.1 here today by finishing up this topic on random variables. We've spent much of our time discussing discrete random variables, and today we're going to shift to continuous random variables. If you recall, with continuous random variables, this is when our random variable can take on an interval of numbers. So we're talking about decimals, fractions, things like that. There are no gaps in between each value of your random variable. Okay, and so when we talk about an interval, this is when we start looking at those density curves, which I know we spent some time on density curves when we looked in chapter 2 at a normal distribution, and we used a lot of those normal CDF features and the table, that's table A, and the formula sheet. Okay, some things we want to keep in mind when we are discussing continuous random variables is they're not really defined necessarily at a specific value when we're thinking of a density curve. We want to really be thinking of this as an interval. So maybe looking for the probability that, say, the birth weight is between two values. And then that'll give us kind of the probability of a range of values. It is very similar to z-scores, and again, the normal distribution that we discussed. If you remember, this was our z-score formula that we had used, okay? All right, we're going to go ahead and actually skip past this example and take a look on the next page at example number 7 here. Okay, and we're going to take a look at just a few different ways of kind of answering these problems here so that you sort of see what your options are in terms of being able to answer these here. Okay, we're talking about the weights of 3-year-old females. It says it closely follows a normal distribution. I'm going to go ahead and highlight that. These are important pieces of information. If we know the shape is normal, sorry, this got blocked out a little bit. It says the mean weight of 3-year-old girls right here, I'll highlight that, is 30.7 pounds, okay? And then the standard deviation is 3.6 pounds, okay? We're going to randomly choose one 3-year-old female, and we're going to let X represent her weight. So the first question is X a continuous or a discrete random variable, and why? Okay, well, we could definitely say that X is continuous. Okay, it is continuous. And our reason is because the weights can span an interval. Okay, and essentially, they are measurements, okay? They're measurements. So we can get really specific and fill in, lots of the gaps. People can weigh lots of different weights, and so there aren't necessarily having to be gaps in between the values here. Okay, now in part B here, we're going to take a look at a couple of different ways to answer this question. It wants us to find the probability that a randomly selected 3-year-old female weighs at least 30 pounds. Okay, you have to be really careful with that phrase, at least. Okay, at least technically means greater than or equal to. Okay, if you think about it like this, if I say tomorrow I need you to bring to school at least $5, I would not accept anything less than $5. I'm really wanting you to bring in $5 or more. So at least means greater than or equal to. Okay. If you recall, they had told us that this distribution was normal. It is always considered extra and excellent communication if you draw a normal distribution and label what the mean is right down the center. Okay, so option number 1 would be to use the table feature, okay, that table of standard normal values which are based on z-scores, okay. If we are going to use table A, we would most definitely have to convert this into a z-score, okay? So what we could do is use our z-score formula. You can see that's up here at the top right here. Okay, the question is, what is the probability that a 3-year-old female would weigh at least 30 pounds? Okay, so I know 30 is going to be somewhere over here to the left of the mean, okay, and we said at least means greater than or equal to, so I'm going to shade that in. I need to change 30 pounds into a z-score. Okay, so I'm going to subtract the mean. I'm going to divide by the standard deviation. That changes this into a z-score of roughly negative 0.19. Okay, that's my z-score. Okay, what I would then proceed to do is I would need to go to the table and I would need to look up a z-score of negative 0.19, and I'm going to go ahead and do that here. Okay, if we were to go to negative 0.19, I think we could see that here on the table. We would be looking at the second to last row where it says negative 0.1, and you want to follow that all the way over to the very last column where it says 0.09, and where those two intersect, I'm seeing 0.4247, okay? 0.4247 would represent that, okay? But please keep in mind that the way the table works is that's calculating the area to the left of the z-score. I'm wanting the area to the right, so I'm really needing to subtract that 0.4247 from 1, and that will give me the area to the right to be roughly 57.53%. Okay, that is one option for doing this problem. Okay, another option is to use the calculator, but to use z-scores. Okay, so if I were going to use the calculator, I would use the normal CDF feature, okay, that we became accustomed to back in Chapter 2. Okay, I would make sure I'm speaking all in terms of z-scores. So my lower bound is my z-score right here, negative 0.19. My upper bound would just be 10,000. Okay, certainly if we go 10,000 standard deviations to the right, we have included everything. Okay, and we end with the mean and standard deviation, but please make sure if we're doing z-scores that you're putting a 0 here and a 1 here, not the mean and standard deviation given to us in the problem in pounds. Okay, if we were to type that in, we would then get 0.5753, exact same answer we got from the table. Okay, a third way of doing this, and I would say this is probably the most efficient way, is to use the calculator, but to use the raw data that's provided to you in the problem. Okay, so I'm still going to use that normal CDF feature, but I'm not going to change anything over into z-scores. I'm going to use the 30 pounds right here. Okay, that's what the data is talking about, the weight in pounds. So my lower is going to be 30. My upper would be 10,000 pounds. Okay, and then the mean and the standard deviation that I would use would be the mean and standard deviation that was provided to us in the problem. Okay, so that would be the 30.7 from the raw data and the 3.6 from the raw data. Now, if I type that in, I get a slightly different answer than the first two. Actually, this answer is the most accurate because these other z-score values were obviously rounded when we type these in. Okay, but we get something very close, and all three of these would be acceptable. Okay, 57.71%. Okay. All right, let's try another one here. Okay, now we're looking for what is the probability that a randomly selected 3-year-old would weigh between 25 and 35 pounds. So again, I'm just going to draw a quick bell-shaped normal curve here. I'm going to go ahead and put the mean down the center. We're looking at 25. I'm just going to put that right there. And then we're saying 35. We'll put this over here. And we're looking for the area in between those. Okay. So again, option 1 is to use the table. Okay, if we're going to use the table feature, we then would go ahead and convert each of the raw data values into z-scores. Okay, you have to have things in terms of z-scores if you are using the table. So I'm going to change 25 and I'm going to change 35 into z-scores. Okay, that makes the left z-score negative 1.58 and the right z-score 1.19. I'm going to go ahead and just squeeze those right in here on the graph so that we can see those lower and upper boundaries. Okay. We would go to the table. Remember, when you're using the table, it's always area to the left. So you want to start with this higher z-score. You want to look up 1.19 in the table. Okay, if we did that, that would give us the area to the left of 1.19 to be 88.3%, but that includes this part as well. So then we look up the z-score at negative 1.58 in the table and we subtract that area off of the 88.30%. Okay, and that would be subtracting this, which gives us an answer of roughly 82.59% of 3-year-old girls weigh between 25 and 35 pounds. This is where we're getting the continuous random variable from. You can see now we're talking about intervals, ranges, values in between. This is all continuous here. Okay, the second method is to use the calculator, but to use z-scores, okay? So we're using z-scores here. I'm going to go normal CDF. Okay, I need to label lower and upper. Okay, we're just going to use the z-scores that we had there, negative 1.58, 1.19, 0 for our mean, and 1 for our standard deviation. We type that in, we get 82.59%, the exact same value we got when we used tables. And then our last option, and again, I would argue that this would probably be the best option to use, would be to use the normal CDF feature, but to use the raw data. Okay, so now we're using 25 pounds as the lower, 35 pounds as the upper, the 30.7 pounds as our mean, and the 3.6 pounds as our standard deviation. And that typed in gives us just a slightly different answer than the first two, but very close, 82.72%. Okay, part D on this, we're looking for what's the probability that a randomly selected 3-year-old girl, that's what X represents, would weigh less than K. Okay, and we're trying to figure out what would be the value, less than a number where 80% of 3-year-old girls' weights are below that particular girl's weight. Okay, I think that you'll find helpful on problems like this if you draw your normal curve and kind of place the information you're given on the picture. It makes it a little bit easier to try to figure out what it is or sort of how to tackle the problem. Okay, so we don't know the weight of the girl where 80% of all of the other girls weigh less than her, so I'm leaving that as a K, but I'm going to go ahead and shade all that area in and kind of label on the picture that 80% of the curve is to the left of that. Okay, remember, there would be two ways that you could do this. Okay, option number one is to think through the z-score formula here. Okay, what we're after is we are after X, which we don't know right now. X is that is really what K is in this particular formula here. Okay, we could go to the table and we could look up in the center of table A where we could find the area to be as close to 80% as possible. If you look in the inside of the table and kind of work your way out, you should find that a z-score that collides with an area to the left of it being 80% would be 0.84. Okay, we're going to go ahead and subtract the mean of 30.7, divide by the standard deviation of 3.6. If we were to go through the algebra then of multiplying both sides by 3.6 and adding 30.7, we end up getting the weight of a 3-year-old girl to roughly be 33.724 pounds. Okay, and that's where the z-score for this is 0.84. Okay, the other option, the other way of doing this is you could use the inverse norm feature on the calculator. Okay, if you use the inverse norm feature, I'm just going to slide this over here. Okay, it looks for 3 inputs here. Okay, you have to designate the area to the left, which clearly would be the 80% for us in this problem. Okay, and we could just use the raw data. 30.7 is the mean, and whoops, I have that backwards here, sorry. Okay, right here I want to put 30.7 is the mean and 3.6 is the standard deviation. If we type that in, that'll give us roughly the weight of a 3-year-old girl where 80% of the other 3-year-old girls weigh less than her. Okay, our very last example here, just one part to this that we're just going to talk through to wrap up this section, is talking about the height of young women. It says they can be defined as a continuous random variable, and they give us the specs here that the shape is normal, that the average height is 64 inches with a standard deviation of 2.7. The question is, what is the probability that a randomly chosen young woman has a height somewhere between 68 and 70 inches? Okay, so again, these are continuous random variables. I'm going to go ahead and draw a small curve here. I'm going to label 68 as well as 70. I'm going to go ahead and shade the area in between there, and I'm going to choose one of the three options up above that we talked through here. I always prefer using the normal CDF feature along with the raw data. We're going to label lower, upper, mu, and sigma. That would be 68, 70, 64. I'm getting that right there, and 2.7. Okay. Once again, if you want full credit on the AP test, you have to label those calculator inputs, or they will deduct for that. Okay. And the answer that we get for this is